Welcome to our first video for exponential and logarithmic functions. We'll focus today on exponential functions. These are great to graph. You've had a sense of the tools already between Desmos and MetaCalculator. Please note that when you're typing in your exponential functions, we don't have a number up here as the exponent. So previously with quadratics, your exponent was a 2 or a 3 for cubic. This now has a base number, and the exponent itself is going to be the x. That's our variable. So we're going to see two different types of graphs. So here we have an increasing function. As x gets bigger, y gets bigger. Here we've got a decreasing function. This sample here is showing us compound interest. So we've already seen that before with bacterial growth. Compound interest, and this kind of exponential function where it's decreasing might be more representative of, like, let's say radioactive decay. So let's take a look at our characteristics here. So x-intercept, where does this graph cross the x-axis? And you can see that I've got it kind of coming down, but it's never going to go across. And you can play with this on Desmos or MetaCalculator. You can zoom out and see if it ever does cross. It might look like it's touching, but it's not. It's just that fine hair above it. It'll never touch. So for x-intercept, we're going to say none. It's really important not to say 0, because 0, that might be the x-intercept, right? It might be crossing at 0. So it's better to just say none. And here for the y-intercept, we see that it's crossing at 3. So we've got a y-intercept of 0 for x value and plus 3 for the y. Now this y-intercept is the a in the function. So as you're looking at a function, so for example, 3 times 2 to the power of x, this 3 is indicated here. If it was -3, then, well, actually we're not looking at those ones. We're just looking at the ones where a is positive. Yeah, so that's showing us where it's crossing. When the base could be, let's say, negative, or less than 1, then we can see a decreasing function. But here we have it where it's greater than 1, and so it's increasing. So for the domain, we're looking for all the x values. We see that every possible x value is associated with a y value. So we're back to x being in the set of all real numbers. And then for range, we're looking at y being everything that's greater than 0. Not 0, because we know this graph never touches the axes, and it never seems to come down here into quadrant 3 or 4 at all. It'll only stay up in quadrant 2 and 1. So y has to be greater than 0. But we don't want to write that little line underneath it. So for end behavior, we're going from quadrant 2 to quadrant 1 as we're swiping from left to right. We meet it here in quadrant 2, and we leave it in quadrant 1. And if it's increasing or decreasing, again, we can look to the base. So if the base is greater than 1, then we would say that it's increasing. In this case here, where we're looking at this kind of coming down, we must have a base that's less than 1. But for our type of functions, we're not looking again at negative ones. I shouldn't have said that. And here, the b has to also be greater than 0. So basically, this should be like a fraction, somewhere between 0 and 1. So if I was to write out a pretend function for that could look like this, I would want it to cross at 2, so I'd put the 2 in the front in the first number. And then the next number, I need the next number, the base, to be less than 1, but greater than 0. So maybe I'll call this 1/3. And it'll have the x as the exponent. Again, we don't have any x-intercept. The y-intercept, let's get it crossing there at 0, 2. So we see that the a value gives us the y in the y-intercept. Domain, same idea. X is in the set of all real numbers. Every possible value for x is associated with the y. And the range is, again, everything that's greater than 0. You can see where these patterns are kind of coming into play here. For end behavior, we're going again from 2 to 1. So that didn't change. But what does change is that we notice as x gets bigger, y seems to be getting smaller and smaller and smaller. So we would call that decreasing. And it's decreasing, if you're looking at the function, it's also decreasing because that base happens to be less than 1. But greater than 0 for our purposes. So have some fun with this one, because there's a little bit of kind of playing around, figuring out the rules with the 7.1 and the 7.2. Enjoy.